Okay, so here's a little bit harder Newton's second law problem. I have here a horizontal table with a 3 kilogram object on it, tied to a string over a weightless pulley, and then attached to a 5 kilogram object. Sitting on top of the 3 kilogram object, there is a 2 kilogram object which is tied to the wall with a string. The 5 kilogram object at the moment is moving down, which means that the 3 kilogram object is moving to the right, but the 2 kilogram object, you'll note, is in equilibrium. The coefficient of friction between the 2 and the 3 kilogram object is 0.2, and between the 3 kilogram object and the table is 0.1. So we'll choose a body. I'll start off and choose the 2 kilogram object as the body. And the forces on it are a tension in this string, which I'll call T1, the object's own weight, which is 20, the normal force, which I will call N2, that's the normal force on the 2 kilogram object, and there is also a frictional force, which I will call F2, which is the frictional force which the 3 kilogram object exerts on the 2 kilogram object. And this is a Newton's first law problem. So the sum of the forces in the y direction equals N2 minus 20, which is 0. So N2 is 20 newtons, which means that F2 is equal to 0.2 times 20, or 4 newtons. Sum of the forces in the x direction is equal to 0, and that's equal to F2 minus T1, and that tells me that T1 is equal to 4 newtons, because F2 is 4 newtons. Okay, I see that I have not chosen where to put these things very well, so let me just move this guy down to here. Okay, next I'm going to choose this guy as the body, and so we have the sum of the forces in the, oh, I better be a little bit careful here. A little bit careful. I'm going to choose plus y to be this way. Oh. Plus y is down. So the sum of the forces in the y direction for this guy. Okay, what are the forces on him? I should say there's his own weight, 50. And then there is a tension, which I should call T2. Okay, that's the tension in the string that goes over the pulley. Okay, and so the sum of the forces in the y direction is 50 minus T2, and that's equal to MA, which is 5A. So let's draw a box around that. There's one equation with two unknowns. Okay. So far we have found out the frictional force on the 2 kilogram object. We have found the normal force on the 2 kilogram object. We have found the tension in the string connected to the wall. And that's about it. Okay, so now we need to carry on, choose another body. So we have the 3 kilogram object. Forces on it are its own weight, 30 newtons. Then there's a normal force on it, which I should call maybe N3. There is the tension T2, which points this way. There is a tension which I should call maybe F3, which points this way. And this is the F3 is the frictional force that the table exerts on the 3 kilogram object. But the 3 kilogram object is also touching the 2 kilogram object. And therefore, we have a force down, which is equal to minus N2 because of Newton's third law. Up here, N2 is the force that the 3 exerts normal to the surface on the 2. So the force that the 2 exerts on the 3 is down this way. And I'll remind you that N2 we know to be 20. Okay. And similarly, there will be a force minus F2, where F2 is, we found to be 4 newtons. Okay. So the frictional force that the 3 exerts on the 2 is equal to the negative of the frictional force that the 2 exerts on the 3. So now we have the sum of the forces in the y direction is equal to 3a is equal to N3 minus 20 minus 30. And that's equal to 0 because this is an equilibrium situation. And so N3 we find is equal to 50 newtons. And so we now know what F3 is. F3 is 50 times the coefficient of friction, which for this guy is 0.1. Okay, so that's equal to 5 newtons. Okay. And so now finally I say the sum of the forces in the x direction is equal to 3a. If I choose plus x to be this way, rule of the finger. Okay, so it'll be the same acceleration as this guy. And that's equal to d2 minus f3, which is 5, minus f2, which is 4. And so 3a equals t2 minus 9. And from up here, we have 5a equals minus t2 plus 50. So if we add those two equations, we get 8a equals 41, or a equals 5.13 meters per second squared. And then we can find T2 from either of those two equations. And when you do that, you will find that it is 24.4 newtons. And that's the end of that problem.